National Center of the Subcommission of Engineering and Technology. He's the counsel of the National Science Foundation and Nanotechnology, and he's the coordinator of the programs of the academic sector. Before entering National Science Foundation, he was a teacher of mechanic engineering at the Kentucky University and also visiting professor in the Institute of California in 88, 89, and John Hopkins 89, 85, 86, and also in Tokyo University and Delphi University. He is credited with 3 interventions. He contributed with more than 200 articles and 16 books, including the flux of particles, nanostructure and technology, social implications of nanotechnology, and lastly, the bioinfocognition in nanotechnology, and also the mapping of nano-knowledge, patents, literature analysis. In 2008, he was a researcher of multiphasic systems, simulation in computers, nanoparticles, and nanosystems. He began the first program in the federal program focalizing in engineering and nanoscale in 1991. He proposed formally that the NNI, with a presentation in the White House in the Commission of Technology in March of 1999. He prepared the National Council of Science in the United States and Technology and reports with nanotechnology and the National Nanotechnical Initiative. He's a member. He is fellow of the American Society of the Mechanical Engineering, and he was a co-founder and president of the AISH and the multiphasic phase, and worked as an editor of a journal, and he is the chief editor of nanoparticles. He has also been a member of the Council in the Americas, Europe, and Asia, and he is in the Risk Council in Geneva. He also made an award at the university in the United States. He was nominated Year Engineer in 1999 and again in 2004 by the Social Professional Engineer Society. He received the Best of Small Tech Award and Forbes recognized him in 2003 as the first ones in the nano power, and the American Society nominated him in 2004 as one of the top 50 leaders in the community of science, and the National Press Club in 2007, and with the leadership in NNI as a individual who is mostly responsible for this nanotechnology. This is a fantastic curriculum. I almost made a conference here with your curriculum, and I would like to pass the floor directly to the professor.
The introduction, and we have some time remaining for presentation after this introduction. Thank you very much. Well, that means I will try to, I was asked to share my experience in establishing this National Nanotechnology Initiative and its management with you, and to discuss especially lesson learned from this experience. Something that you might find of interest, that National Nanotechnology Initiative is now the second largest national research program in the history of the United States after Apollo program in cumulative way. That means if you cumulate the 10 years investment. Another aspect that is quite interesting is that is the only program that was primarily justified by basic science. All other programs were justified by societal needs. In my presentation, I will try, in fact, to make a few points. First point will be that in the last 10 years, nanoscience and engineering are on the top of the wave of discovery and innovation. And now we have a significant progress in new phenomena, inventions. You have even products that can be about listed to more than $200 billion incorporating nano. However, in 2010, we are still in the formative phase of nanoscience and engineering for several reasons. We just now enter direct measurements. We do only indirect measurements. We have only empirical method in processing and manufacturing. Most of the products are very simple, nanolayers dispersions. We are now entering systems. And the focus of research in 2010 is switching now to more science-based, to systems, to more complex, revolutionary new products. And I estimate in the next 5 years will be the most active time for research, because now we have more elements to work with to go to systems and new products. And a last point that I would like to make is that by 2020, nanotechnology will be a broad-based technology in industry, medicine, with mass use. And because of its societal implication, will be a need to institutionalize research, education, manufacturing methods, addressing societal implication. That means at this moment in most of the countries, we address nanotechnology with ad hoc programs. For instance, we have a research program for 2-3 years. We have a small improvement of existing law, but this will not be sufficient by 2020. Now, I think this is working. Okay, I have to show the direction. First point that I like to make, which is a serious point, is that media was dominated in the last 10 years basically by extremes. Some people were claiming the nano will change the human body, how is suggested by that picture, or even mind. People speak about transhumanism because of nano. And other people are afraid of each consequence of nano. Even if nanotechnology replacement is a better environmental or societal solutions than existing technology. And in my presentation, I will try to stay on the core between these two extremes that dominated the media. Okay, how to do it? All right. If you look in the last 10 years, in 6 major indicators for nanotechnology, the number of people involved, the discoveries represented by papers, invention, innovations, final products incorporating nano, research and development funding, and venture funding, you find between 2000 and 2008 was an average growth about 25% per year, which is quite impressive. That means each 3 years we double. However, In 2009, we have a kind of crisis, and the rate continue to increase overall in the world, but at a rate less than half. And what is most interesting is that from this crisis, some countries came out very well, others have suffered and even declined the outcomes. So it's a kind of an uneven result from this crisis. Also, if you look, in 2000, we made an estimation that by 2015, we'll have 2 million workers and about 1 billion products. If you continue by the same rate, 25%, the existing rate that was observed in the last 9 years, you get exactly on these numbers, more or less. That means it will not be exact number, but that means if we continue to increase by 25% per year. You see that by 2020, we'll have about, if we continue this 25%, we'll have about $3 billion products. To take the context, it's all right. Nanotechnology is developing in the context of emerging technologies. And again, when we started to look to nano, we looked to 5 areas. We looked certainly, information technology was better established, bio, which was better established, but not organized in a single coherent program. National Nanotechnology Initiative took the initiative on material world, and cognitive science is that it's most behind. That means this will be probably the next major mega trend in research related to cognitive sciences and cognitive technologies. And certainly all are connected through a system approach. Okay. If you look now in the context of the United States, as I mentioned before, you find that National Nanotechnology Initiative is the only initiative that was primarily motivated by fundamental research and is organized from bottom up. What means this? It is not organized by any other previous projects from top down with a fixed amount, with a top-down management, but is organized by components, by projects that each one is justified on its own merit, and thereafter they are assembled to create the system. You can see that all other programs were more centralized and were primarily motivated by societal needs. Could be competition, could be international agreements, could be the needs in industry. In NNI, when we started, basically we have 2 main reports. One report was based on a benchmarking, what happened around the world in the field of, now we call nanoscience and engineering. And secondly was a report on looking 10 years ahead from 2000 to 2010. What is interesting, if you read this report that was written 10 years ago, is still actual, because it was written at a conceptual level, not looking to the basic conceptual ideas and potential developments in long term. Concerning nanostructure science and in technology, one main outcome was a definition for nano. In 2000, the definition was quite different in different countries. For instance, in Japan was nanoelectronics devices on surfaces. In Germany was ultra-precision engineering. In Russia was ultra-dispersions. That means all were based on one application, basically. Now, what we've done by this definition, we told is not none of this. It's the transition between single atom or molecular behavior to collective behavior, where all properties and functions are defined and can be changed easily with a small amount of energy effort if you know how to do it. And that means what is the essence of nanotechnology is a natural threshold that happened from single atomic molecular behavior to collective behavior or bulk behavior. That means this happened in nature anyhow, but we didn't have the control. Even more, because we don't have the instruments to measure and the theories to develop. All the time, we assume it's a continuum transition. In fact, this is a discontinuity in properties and function at this level. And that means the basic idea was to exploit a natural threshold that happened in nature for industrial or medical purposes. In the vision, that was the next document, we look to two main goals. One is to change the foundation in science and technology and medicine from micro, where all properties are fixed and defined, to nano, where all properties can be changed systematically from bottom up, again, if you know how to do it. Secondly, to create a general purpose technology, similar how information technology is taking shape. That means you use the same concepts, the same principle in different areas. For instance, to give a simple example, you use the same instruments to measure the structure nanoscale in medical field, or in ceramics, or in environment. And the same knowledge can be transferred, and you have a lot of innovation and new ideas. And what was more important was that we look, that means to exploit these new phenomena, we look to generality of science and engineering at this level. We look to create the most efficient length scale for manufacturing once we develop the knowledge. And in that report, we look to 10 areas, how they will change in 10 years. I'd like to mention this year, after 10 years, we made the record what happened in the last 10 years. We developed a new vision for next 10 years. The draft is on the web, and I will mention immediately. What was the process to now to go from these concepts to effective implementation? That means we prepared like a science project, different dimension of a national activity. We developed a long view that was a research direction. We done benchmarking. We looked to grand challenges for United States. We looked to societal implication. We have even a material for the public to involve. We sent to 30,000 schools a brochure called Reshaping the World Atom by Atom. And we developed, in fact, a management program from bottom up with different time scales and 4 levels of management. Was this 10, 20 years vision, was a strategic plan each 3 years, each year a budget, and each month a decision done by the interagency group. What was the idea now from the technical point of view in long term? The idea was that you need about 10 years to develop the foundation and to develop science-based processes and to develop the first products based on this new phenomena that are discovered. And that means this 10 years was 2000, 2010, where basically, as you know, we use indirect measurements like atomic force microscopy, which are very rough measurements because millions of events, tens of atoms on a surface. That means basically you don't learn anything about the phenomenon itself. You learn an integrating result. Secondly, we have only empirical correlation in manufacturing. If you look, even the most simple process in aerosols, anything is based on some previous experience. You put a coefficient of 10,000 for nucleation. and you do not understand what happened, but you do develop different processes. That means it was a necessary step in any new development to go through empirical phase. And certainly the focus was to create a library of particles, quantum dots, nano layers, and eventually to start to go on as a periodic table to see what each element what can do. And we discovered that now we can do nanotubes from 20 elements. We can obtain magnetic properties from other 30. And that means, and we are still advancing and we try to exploit them. Now, second phase will be when we start now to do direct measurements. For instance, you have a measurement done at Caltech that you track where each atom is going at a femtosecond during a self-assembling or a chemical reaction. Eventually, we look to collective effects and to create nanosystem. Nanosystem cannot be created only by trial and error. Combinatorial approach is not successful. Combinatorial approach is successful for nanoparticle or quantum dots, but not for system. So you need to go to a more simulation-based, science-based approach. And the focus in the first 10 years was mainly to create the infrastructure, partnerships, workforce. The new focus now is to look which are the new disciplines that we create. For instance, synthetic biology, or we see neuromorphic engineering, create new fields, new industries, and societal impact. That means more and more, because it's broad impact, nanotechnology becomes like a socio-economic project, because it's no longer driven only by the scientific event. Okay. In the US, we have a report about the importance of application versus basic understanding, and we have these four approaches. If you look to application, we have certainly Edison approach, when we have large application done by trial and error, but you have not good understanding. In first 10 years, basically our focus in nano was so-called Bohr approach. We look for scientific discoveries, but not so many applications. As we move now, the 2010, we move to science-based, application-oriented approaches. I mean, so-called Pasteur quadrangle. And I think this is more and more required by society. As you know, in all countries now, we are required to show results from research, and we start to have the tools to produce these results. In more details, we look, in fact, that we have a continuous increase in complexity, dynamics, interdisciplinarity, uncertainty in time. And we told that in 2000 we start to create the first passive nanostructures, I mean structures that do not change their properties and function during their use, like a nano coating, like quantum dots. And we start to create systematically such kind of passive nanostructure. In 2005, this was a estimation made in 2000. In 2005, we told that will start to appear active nanostructures that change their behavior during and composition during their use, like drug delivery, like sensors with actuators, like transistors. And in fact, this happened. And thereafter, in 2010, now we start to move for the first time to build revolutionary new products. It means build on a new system that was not known before. That means in the first two phases, we use existing systems. For instance, we use a polymeric material and we put nanoparticle to improve the properties. It means basically, nanotechnology offers an improvement in an existing product, but it's the same product. And as we advance after in 2015, 2012, we start to reduce the size of these devices to macromolecule or nanoscale component. Just to observe this transition between first phase and second phase, that means between passive and active nanostructure, we plotted the papers published in active nanostructures, and we found that suddenly about 2005, 2006, the number of papers doubled per year, arrived to 11%, and in 2008, double again, showing the introduction, basically, a larger scale of this more, I will call, more complex nanostructure like self-healing materials, targeted drugs, energy storage, and other elements. If you look now for the second threshold, where I should direct this?
Next.
Okay. This one. Okay. If you look now for, in 2010, we found that industry started to look to nanotechnology as a major opportunity. And we have a survey from manufacturing industry, and they surveyed 270 companies. And about half of them, basically they told in about 2011, will have either a product or something in design related to nanoscale science and engineering, which is a major advancement if you consider that in 2000, almost zero would have been the result of this survey. That means we have a significant change in this threshold of 2010. Many people would like to ask, what are these third and fourth generation? I give several examples that are all now in advanced research, like artificial organs. For instance, you start from the subcellular level, and you build the tissue, and you build the blood vessels and the scaffold. It's bioassembling, for instance, using viruses, is fluidic assembling, printing. Sensor system with reactive mechanism, robotics on surfaces, designing of new molecules to self-assemble or to do different functions from those known in their nature, hierarchical self-assembling, and many other areas. In 2010, we realized that we have a kind of loss of steam in research, because many people told, oh, we do nanoparticles, we've done this for 10 years, what is the future? And we decided to assemble again a group of experts and look again for 10 years to look for a vision for up to 2020. And we done this, and in fact, the goal was to look what was the real effective progress made in last 10 years, what are the research direction for next 10 years, to redefine in a way the focus in research and what is nanotechnology. That means no longer these components, but something different. And how to institutionalize the advances, because we cannot progress on this large scale only by having 2-3 years programs, ad hoc programs. And how to address public acceptance, education, manufacturing. And NSF took this study. We have, in fact, 5 meetings around the world. One was in Hamburg with all Europe. One was in Tokyo with Korea, Taiwan, Japan. One was in Singapore with China, India, Australia, and other back in Arlington. And basically, we surveyed all major countries that do nanotechnology and leading experts. And so we surveyed basically 35 countries. And we created an open source material that is on the web. You will find, and I will give the website immediately. Also, in part of this study, we track what happened effectively with investments made by governments by considering these definitions that we have that has to be a new properties, new functions. It means we eliminated the research that sometimes governments they work in materials they call nano, or they work in microelectronics they call nano. We look only to research that is based on a truly new phenomenon of behavior as an intermediate length scale between 1 and 100 nanometers. And you observe that in fact, we start to track this directly in '97. In 2000, after the speech sent by President Clinton, you see the change, this effective investment made by countries in the past. But what is most interestingly now is that in 2006, when we moved to next generation of structures, active nanostructure and devices, the rate of investment has increased, not decreased. People expected that after 4 or 5 years, this will flatten. The reason has increased is that new domain center, new lateral domains like agriculture, like health, like energy, because new countries have entered the game. For instance, this increase is mainly after 2007, 2008 is caused by Russia, Iran, European Union that made a 20% commitment. That means new countries that were not in the play in the first 5 years. And if you look now in 2008, then the data are certain. 2009 are still not very clear in all countries. We have the following statistics. We find that in US, we have about $5 per capita used for nano. In Japan, $7 per capita. In Korea, 6. China is much lower. However, they buy much more research with that money. And in fact, China has about the same number of researchers as the United States at this moment in nano. They are much more at the beginning of their career, and they don't, their work is not cited so well, but they have about the same number of papers as the US. When just 7 or 8 years ago, China was less than 10% of US, just to see the level of investment and rapid development. Also, another interesting fact is that industry, that means initially in 2001, governments were spending more than 10 to 1 compared to industry. Slightly, industry invested more and more in basic development, mainly basic pre-competitive research in this field, and in 2007 has exceeded worldwide the government investments. This is a trend that shows that industry is part of the game now. If you look now to US, it's interesting that in 2000, we told that the research investment made in nanotechnology in US will increase by 20% per year for 10 years. And at that moment, there were very few people who believe in this. At this moment, the average rate of increase is more than 20% per year. It's a sustained development. As I mentioned, we are still maybe halfway in the long-term view. And you see, US has now roughly about $1.8 billion, which are mostly pre-competitive funds. I mean, it's a difference from Korea or Japan, where at least half of the money are in application-related projects. At NSF, that initially started the project basically for 3 or 4 years, we developed these concepts, and after certainly we developed at national level. The focus is on fundamental research. Now we have about 5,000 active projects in nano, establishing infrastructure, we have about 26 large centers and several user facilities. And we train about 10,000 students per year. In environmental health and safety, we spend about 30 million per year. This is certainly more basic research. That means we deal more with developing the understanding the transport of nanoparticles in soils, for instance, in understanding the nanocolloids in interface with the skin, but we do not go in application project where there are specialized agencies in the United States to do this. If you look to this societal dimensions, it is very important because without this you do not have safe application, you don't have acceptance. We look, this is a percentage of the budget of NSF spent in this area, societal dimension, since 2001. You see that for blue, which is environmental health and safety, we have now about 7 to 8%. For education, we have other 7 or 8%, and for ethical, legal, and other social aspects, about 1, 2%. Maybe to make a point that you see here, EPA start to invest. NSF started in 2001, has about 40 projects in 2001, 50, 55, 60, and increased. Now it's about roughly 100 projects per year. EPA entered the investment in 2003 with so-called STAR program, NIHs in 2004, and DOE, FDA in 2005. Means mission-oriented agencies now are very active, in fact, and they play the dominant role. If we look to the number of papers that sometimes I mention, paper alone is not enough. One has to look to the quality, citation, and other elements. However, looking to the number of papers, you find that this is, blue line is United States. You see, between up to 2005, United States was focused on grand challenges. In 2006, the recommendation was to, from top down, was to move the programs in the core. The result was a reduction of the output. Maybe has an implication in other fields, but this is an example to see how decision in governance affect the outcome in a country. This green is European Union that continue to have a large output as number of papers, and they continue as interesting. Even in this time of crisis, they have 20% increase in investment in their plan for nano. This is China, the red, and the blue one on the bottom you see is Japan. Japan more or less is constant after 2006, 2007. If you look now to the quality, and I choose to be less subjective, just 3 major journals, Science, Nature, and Academy Proceedings, you find that about 65% of paper have the first author from US. From China, it's 3-4%, even have the same number of papers as US total. You see Germany is about 14%, and France and Japan immediately after. I mean, this is an important comment that quality has to be certainly taken seriously in consideration, not only number of papers. Now, if you look to focus, to look to the context, if you look in United States, this is material science, chemistry, physics, where nano it is. you find the United States more focused in life science, environmental science, and the relative focus as compared to all the fields is not so high in physics and chemistry, mainly because it's United States has a long-term view, long-term inertia, also from previous of the cluster to be modeled from basic principle by more than 10 times per year, and will become an essential element in design. Direct measurements will be able to increase the brightness in light sources and X-ray about 6,000 times. That will allow to go to larger domains to investigate and to shorter time of resolution time. With a shift from passive to active nanostructure nanosystems, we have more and more a focus on self-powered, which is essential element, self-repairing dynamic systems. Nanotechnology is entering in large scale, more than 30% in catalysts, more than 30% in electronics, and platforms are created. Nano-EHS will become more integrated with nanobio core research and moving to more predictive approaches. We move more to personalized nanomedicine. Energy, it's interesting. Now it's not economic, at least in the US, it's several times more expensive than regular energy. And so by 2015, we expecting breakthroughs that we don't have yet at hand, but expecting breakthroughs that, based on what happened in the last 2-3 years, will have economic application of solar energy. We'll have more and more integration with bioinformation and cognitive technologies. It's more and more important to do horizontal, multidisciplinary, vertical, from elementary to graduate school integration in education. And for governance, is a need, as I mentioned before, to institutionalize nano. Several fast examples. For instance, is a need still to discover basic phenomena. I take an example here, then interaction forces at nanoscale provide a repulsion between surfaces if the materials are properly selected in a nanosystem, and so it's a kind of lubrification force, and so the concern about high friction of nanosystems can be avoided. This is a kind of history, what happened in the last years, last 20 years, in fact, in increasing power of computers. And here you see that in the last 10 years, we have an improvement factor of a simulated structure about more than 10 times per year. That means each year we can simulate 10 times more atoms with the same methods. We have first devices, as I mentioned before, to look to femtosecond for large areas. Here, this doesn't work, but it's a surface of graphite. And you see the time scale of the process itself, you see fluctuating like a heart. And you can see each atom in this structure, what is the dynamics. If you look to the direct measurements using X-ray or other sources of radiation, you find that the power of penetration increased significantly. And if you compare it to the Moore's law, which increased 2 order magnitudes in the last 10 years, X-ray brilliance increased 3.6 means order, so magnitude means much faster. And this is expected to continue. We look more and more as an example for system to create platforms where, for instance, you have in this case to transform mechanical energy in electric energy at the nanoscale and to be used in different systems from laptops to medical devices. But more and more that means you look to self-powered system. We start to create platforms. As an example, platform based on product developed in the United States in the last year. For instance, we created rolls, tapes, and this can be used in satellites, can be used in airplanes, Many of these are not economic because are not done on a large scale. However, for satellite are very economical at this moment already. That means by creating these platforms, you can advance faster and develop benefits from different industries. You see that these have different applications, both in civilian and in defense in this case. Also, something interesting is that I use this slide to mention that in semiconductor industry, in 2000 we have 0 nano. In 2003, we have the first introduction of nano layers in processors. By 2010, worldwide, about 30% of production using nano is a condition for development, and by 2020, almost certain it will be 100%. Another example is nanotechnology for aerospace. That means nano will allow to create, now in fast development, composite materials that would have very good, will be lighter, will have very good thermal insulation, good for vibration, and so will allow to bring the engine close to the main body of the plane. And we have several projects, some advanced. It's a kind of very nice integrative approach. We have 6 or 7 core applications of nanotechnology. And we have a project already for a plane that probably will be effectively commercialized in 2030 that will have the consumption of energy about half of the best, most efficient plane now, Boeing 777 as a base. This is a plot showing where we have the cost of energy. This is a cost from coal of energy in the United States. This is a cost from solar in the house. That means you see it's very expensive. That means only if you have subvention and society is wasting a lot of money now, you do solar energy, because in other countries could be a different situation, but in average, this is the United States. But you see, we expect by 2015-16 to become economic, which would be a major development. And so at that moment, solar energy can be applied at large scale. Another important field that was identified certainly is sustainable development, by considering that every major ecosystem is under threat now, is not sustainable. You don't find any prime mineral resources, climate, energy, biodiversity. The issue is only when will become a critical moment. And so nanotechnology may offer breakthrough solutions. That means it's one of the few alternatives. That means in other cases you take one solution from one field and move in another field, but you create a, for instance, for food, we can create fuel from corn, but thereafter we have a crisis for food, and the cost for food is increasing. However, nano is offering the breakthrough solution. To give an example, in the United States now, in energy, water, from all projects, 70% of solutions are coming already from nano in research. And probably this will be even higher in the future. Also, we have to move more and more to predictive approaches. This is an approach adopted by Center of UCLA, one of NSF centers created about 3 years ago, where this is part of this report that I mentioned for 2020, an approach that you try to identify the most critical elements to find the most important pathways for toxicity and to address them. Even more importantly than these isolated fields, we find that nano is at the core of converging emerging technologies. For instance, quantum information system is not possible without nano combining with information technology and other fields. Eco-biocomplexity, neuromorphic engineering, cyber-physical systems, synthetic and system biology, cognitive enhancers. And I have a list about 30 domains that were created in the last 10 years and all have high promise. And this is changing sometimes even the ethics. I recall that when we proposed, I had in 2001 a report, Converging Technologies, and there I wrote that would be brain-to-brain interaction without sensors. At that moment, most of the comments in the media was that this is not only science fiction, but it's against the human nature, that we speak about controlling mind and so on. Now you know that in 2010 we have this. Without intruder, you put something over your head and you can communicate. This is partly because of the nanotechnology. Also, nanotechnology are allowed to have portable devices for learning, for communication. But the point is that nano is enabling a new way to do things and eventually changing not only the quality of life, but may have affect sometime even the acceptance of technology in the future. If we look to the governance, we look to nano in a quite systematic way in 2000 that I think pay off. In time this was diluted because of the, you have many players, you have a political environment, but we told that we have to combine visionary, transformative, responsible, and inclusive method all in the same time. And for instance, for transformative, one has to look to focus on tools, infrastructure, innovation, and to exploit the properties and the specific particularities of nanotechnology that is multi-sector, multidisciplinary to develop this. When you speak about responsible, one has to look, first of all, how you invest the money. Some people, when you speak about responsible, think about toxicity. That is a very important issue, but it's not the most important issue. It's a key important condition. But the first condition is where you invest the money. You put in water, you put in energy, or you put in cosmetics, for instance. This is a major question, first question. And that means one has to look, when you speak responsible, not only to risk. And we speak also inclusive, we include different disciplines, inclusion in economy, international. That means we have to involve different stakeholders. And these are just I show for illustration. This is done by Georgia Tech. They look how the papers published in Nano are crossing different fields. And basically, they determine that this is more interdisciplinary than most of the emerging technologies that are developed in parallel. You see the material science still has a large part, chemistry, biomedical research, engineering, physics, geosciences, and this is a reflection of this evolution in interdisciplinarity. Another aspect, for this inclusive aspect, is international collaboration. It's interesting, up to 2004, most of the collaboration are bilateral or trilateral, small organization. In 2004, we organized the first so-called international dialogue. We invited 26 countries and EU, and basically we developed a kind of community that has several spin-off activities immediately. For instance, immediately we created an occupational safety group. OECD created a working group. We created activities in ISO. That means in an interval of just 6 months or 1 year, we have about 10, 12 activities in international organization, and these are continuing now. One reflection of this interaction, in fact, is not to do by measure from top down, but to do by building the capacity. And I show this picture from the Network for Computational Nanotechnology. These are their users. Think what is the better way to connect the community, by a decision or by a paper or by creating this ability to them to collaborate instantaneously. Basically, each light show the intensity of the light show users in different parts of the world. And it's interesting, all are connected almost simultaneously. For instance, many of them work on the same project. Someone puts the computer code on the framework. And immediately, in about 2 weeks, someone is using their experiments to improve it and put the improvement. Or you find courses that are improved continuously. It's a kind of open source, open contribution in this field. Now, something that anyone is interested in, what is the total return? I made this, I do this in each year since 2000, and certainly this has some approximation, but I look to the major inputs and outputs. And this is similar to chemical industry. Chemical industry is doing this each year in the same way. And I look in 2008, when we have certain data, we find that industry put about 1.9 billion in research and development, government put 1.5 billion, and finally we have about 80 billion products that were surveyed by industry. Again, these are relatively simple nano components incorporated in products, and we look to the products that have a condition for their performance and efficiency and competitiveness to have the nano components, but still it's a large number. This is about 150,000 jobs. And if you pay back taxes and research and development still remain with a surplus that partly has to go back to the operating cost of the industry. That means if you look now, what can be done in the future at the international level? More and more we have to recognize that the system is not a system that can be controlled by a single organization like United Nations or a single country, but is a dynamic ecosystem, self-regulating ecosystem, and our role is to create capabilities, directions. For instance, one is to create this open source model, incentive-based mechanism to go in, for instance, in the direction of sustainable development in this global self-regulating ecosystem. Other approach specific for nano is to create these multidisciplinary, multi-sector platforms that will create a lot of synergy and innovation. Other thing is to develop institutional capacity to address the future development, including in toxicity, including in social events, including in economical aspects. Other thing we have to develop, we don't have now a global communication system to cross the fields, to cross organization, to cross, for instance, researcher to legal system, to industry. At this moment, we have still a fragmented information system. And certainly, we have to implement using adaptive long-term planning. This is difficult to be done because most of the organizations do not like to have a long-term plan because it's a risk also impose some commitments. And a risk not to be true, usually it's very difficult to be done, cannot be done by low-level administration, how sometimes happened in many organizations. You have a strategic plan, you give it to a contractor, and he doesn't know anything about you, has some technician, and they come back with a plan that basically doesn't have much value. That means usually it's a difficult operation to do this. Now, if I have a conclusion, that means for the next 10 years, nano will have an effect, especially one of the main benefits will be knowledge progress by developing our comprehension of nature, underlying science in industry. Other will be the so-called economic material progress. That means why we do nano? We do because it's more economic, it's more efficient, can do things that cannot be done before. Other will be the global progress. And here, this global progress will help human development, like health, sustainable, international collaboration, and certainly moral progress even. We look to have better access to healthcare, to quality of life, equality. That means These are several of the goals of humanity, but I'll try to show how the technological field can address these long-term humanity development goals. In closure, I like to tell that nanotechnology now in 2010 is having a major shift from empirical to science-based methods, from components to systems, from science discovery to technological innovation in applied materials, in electronics, pharmaceutics, chemicals, is expanding in other new fields like very fast, like agriculture and food, like energy, like water filtration, like modeling and simulation. And this happened on a global level, as you know, and a fast pace. And so it is more important to have an international governance approach for this large self-regulating ecosystem in order to be sure that we have the best results in human development and with a minimum risk. And I like to acknowledge that Brazil made significant progress in the last years, and I like to congratulate, including this conference that shows a foresight and the concern about the future. And at the same time, I like to acknowledge that the potential for Brazil probably is much larger, especially in this combined science, technology, economical impact, and including international participation in the development of nanotechnology. Thank you very much for your attention. So one will be the first product. However, in 2002 in the United States, 2001 we formed an association, Nano Business Alliance, and many companies in 2002, 2003 entered the field with research and investment activities. And this was faster than expected. The result of this was, in fact, that one thing that looks normal now, in 2000 people predicted that Moore's law for electronics will flatten, will not continue because we reach the limits of physics. And because of this research, one of the, just an example, the Moore's law was unaffected in the last 10 years. That means at that moment we expected that this will not happen. Discoveries in several fields like plasmonics is a completely new field, interaction of photon with metallic interfaces, but it means basically was not expected like a field. Metamaterials, they have a reverse index of refraction. Spintronics was just started. We have the major workshop in 2001. Graphene, as you know, in 2004 was put on the map. Cancer detection and treatment, we planned for this, but we thought that by 2020 we'll have the first detection of cancer methods approved by FDA. In fact, now we have many that deal also with treatment, drug delivery, and we have new fields like synthetic biology that is a result of nanocontrol, neuromorphic engineering, nanocontrol as a neural system, quantum information systems that is very important now. And also the formation and strength of international community, including in nano-EHS, especially in the last 3-4 years. Now, if you look lesson learned that anyone likes to look to this, I limit to 3. First of all, we noted when you do not have a vision, you don't have a direction, conceptual direction, the results are not as positive as you have one. And so we still need to develop the theory, direct measurements, direct simulation, and focus programs in order to maintain the rate of discovery and to have the results desired for application. I mention this because some people consider that once we build empirically some nanoparticles, the field is done, it's finished. And so that means this is one very important conclusion. Besides nanostructured metals, polymer, ceramics, other fields in classical industry can provide excellent opportunities, such as textiles, wood and paper, agriculture, food. And consortia with these industries, together with public funding, are the best way to address these generic topics. And another comment is we need to increase the multi-stakeholder and public participation. This is a major issue in order to have public acceptance, funding, and including acceptance from the point of view of nano-EHS. I'd like to make a following comment that if you ask someone directly, you tell, are you afraid about nanotechnology? Probably 70–80% will tell, maybe, yes, I don't know. However, if you ask people, we have these 20 major technologies, from car industry to, let's say, tobacco to up to cancer treatment and nanotechnology and biotechnology. How dangerous they are? You find the nanotechnology is just in the middle of all of this. That means it's not certain. That means sometimes, because of the attention on nano, people try to download all the danger of emerging technologies on one single question. But one has to be very careful to look in a nuanced way. Now, we are in 2010. As I mentioned before, I think that we are still in the formative phase, and I take only a few arguments. We are still characterize the particles like in micro and macro domain. I mean, we look to shape and size, which is totally unnatural for nano. We have to look to internal structures that give all the properties and arrangements, maybe at least number of atoms on surface. And this start to be done, but it's interesting, after 10 years, we are still so much behind in this element. In measurements and simulation, as I mentioned, that only last year we have done the first measurement of a domain of biological or engineering relevance with atomic accuracy and femtosecond at the time scale of the process itself. In manufacturing, most of the methods are fully empirical, some are semi-empirical, and use only one chemical because of lack of knowledge. We use only one chemical component to create nano, and we look only to steady state. This is a very big opportunity because this will lead to manufacturing and production. In products, most of the products, including transistors or catalysts, we use nanolayers or dispersion of particles, which are very simple nanostructures. And this shows that we are very much at the beginning. Basically, we are not in an advanced phase. And certainly, knowledge for risk governance, including nano-EHS, is also the beginning. For this reason, we've done these studies that I mentioned before. Let's see. No. That you find all the results on this website, wtech.org nano2. What you'll find there, you find certain areas that we look, what are the major results in the last 10 years? What are the expectation priorities for next 10 years? And I summarize in one slide these 450 pages that you find there. First of all, in theory, modeling, and simulation, we found that almost certain will have at least 1,000 times faster simulation and will be able to increase the size of the cluster to be modeled from basic principle by more than 10 times per year, and will become an essential element in design. Direct measurements will be able to increase the brightness in light sources and X-ray about 6,000 times that will allow to go to larger domains to investigate and to shorter time of resolution time. With a shift from passive to active nanostructure nanosystems, we have more and more a focus on self-powered, which is essential element, self-repairing dynamic systems. Nanotechnology is entering in large scale, more than 30% in catalysts, more than 30% in electronics, and platforms are created. Nano-EHS will become more integrated with nanobio core research and moving to more predictive approaches. We move more to personalized nanomedicine. Energy, it's interesting. Now it's not economic, at least in the US, it's several times more expensive than regular energy. And so by 2015, we expecting breakthroughs that we don't have yet at hand, but expecting breakthroughs that, based on what happened in the last 2-3 years, will have economic application of solar energy. We'll have more and more integration with bioinformation and cognitive technologies. It's more and more important to do horizontal, multidisciplinary, vertical, from elementary to graduate school integration in education. And for governance, is a need, as I mentioned before, to institutionalize nano. Several fast examples. For instance, is a need still to discover basic phenomena. I take an example here, then interaction forces at nanoscale provide a repulsion between surfaces if the materials are properly selected in a nanosystem, and so it's a kind of lubrication force. And so the concern about high friction of nanosystems can be avoided. This is a kind of history, what happened in the last years, last 20 years, in fact, in increasing power of computers. And here you see that in the last 10 years, we have an improvement factor of a simulated structure about more than 10 times per year. That means each year we can simulate 10 times more atoms with the same methods. We have first devices, as I mentioned before, to look to femtosecond for large areas. Here, this doesn't work, but it's a surface of graphite. And you see the time scale of the process itself, you see it fluctuating like a heart. And you can see each atom in this structure, what is the dynamics. If you look to the direct measurements using X-ray or other sources of radiation, you find that the power of penetration increased significantly. And if you compare it to the Moore's law, which increased 2 order magnitudes in the last 10 years, X-ray brilliance increased 3.6, means order, so magnitude, means much faster. And this is expected to continue. We look more and more as an example for system to create platforms where, for instance, you have in this case to transform mechanical energy in electric energy at the nanoscale and to be used in different systems from laptops to medical devices. But more and more that means we look to self-powered system. We start to create platforms. As an example, platform based on product developed in the United States in the last year. For instance, we created rolls, tapes, and this can be used in satellites, can be used in airplanes. Many of these are not economic because are not done on a large scale. However, for satellite, are very economic at this moment already. That means by creating these platforms, you can advance faster and develop benefits from different industries. You see that this have different application, both in civilian and in defense in this case. Also something interesting is that I use this slide to mention that in semiconductor industry, In 2000, we have 0 nano. In 2003, we have the first introduction of nano layers in processors. By 2010, worldwide, about 30% of production using nano is a condition for development, and by 2020, almost certainly it will be 100%. Another example is nanotechnology for aerospace. That means nano will allow to create, now in fast development, composite materials that would have very good, will be lighter, will have very good thermal insulation, good for vibration, and so will allow to bring the engine close to the main body of the plane. And we have several projects, some advanced. This is a kind of very nice integrative approach. We have 6 or 7 core applications of nanotechnology. And we have a project already for a plane that probably will be effectively commercialized in 2030 that will have the consumption of energy about half of the best, most efficient plane now, Boeing 777 as a base. This is a plot showing where we have the cost of energy. This is a cost from coal of energy in the United States. This is a cost from solar in the house. That means you see it's very expensive. That means only if you have subvention and society is wasting a lot of money now, you do solar energy, because in other countries could be a different situation, but in average, this is the United States. But you see, we expect by 2015-16 to become economic, which would be a major development. And so at that moment, solar energy can be applied at large scale. Another important field that was identified certainly is sustainable development, by considering that every major ecosystem is under threat now, is not sustainable. You don't find any mineral resources, climate, energy, biodiversity. The issue is only when will become a critical moment. And so nanotechnology may offer breakthrough solutions. That means it's one of the few alternatives. That means in other cases you take one solution from one field and move in another field, but you create for instance, for food, we can create fuel from corn, but thereafter we have a crisis for food, and others, or the cost for food is increasing. However, nano is offering the breakthrough solution. To give an example, in the United States now, in energy, water, from all projects, 70% of solutions are coming already from nano in research. And probably this will be even higher in the future. Also, we have to move more and more to predictive approaches. This is an approach adopted by Center of UCLA, one of NSF centers created about 3 years ago, where this is part of this report that I mentioned for 2020, an approach that you try to identify the most critical elements to find the most important pathways for toxicity and to address them. Even more importantly than these isolated fields, we find that nano is at the core of converging emerging technologies. For instance, quantum information system is not possible without nano combining with information technology and other fields. Eco-biocomplexity, neuromorphic engineering, cyber-physical systems, synthetic and system biology, cognitive enhancers. And I have a list about 30 domains that were created in the last 10 years, and all have high promise. And this is changing sometimes even the ethics. I recall that when we proposed, I had in 2001 a report, Converging Technologies, and there I wrote that would be brain-to-brain interaction without sensors. At that moment, most of the comments in the media was that this is not only science fiction, but it's against the human nature, that we speak about controlling mind and so on. now you know that in 2010 we have this. Without intruder, you put something over your head and you can communicate. This is partly because of the nanotechnology. Also, nanotechnology are allowed to have portable devices for learning, for communication. But the point is that nano is enabling a new way to do things and eventually changing not only the quality of life, but may have affect sometime even the acceptance of technology in the future. If you look to the governance,